Hi learners, and welcome to a natural sciences lesson. So today we are still dealing with our expansion and contraction. However, we are going to be looking at the practice questions that are based on that particular topic, expansion and contraction. So let's start. The first question that we have, it says that we need to compare the expansion of different solid materials by drawing a graph. So we have different materials. We have 1, 2, 3, 4, 5, 6 different materials, and then the expansion when the temperature is increased. So we need to compare the expansion by drawing a graph that is suitable for this particular scenario. So remember that we can either draw a line graph or a bar graph. However, the difference between those two graphs is that a line graph, it shows a continuous relationship or a continuous increase or a continuous comparison between particles or between substances. Whereas here, we have different groups of particles or different groups of material that they are not similar to each other. We have brass, iron, steel, so we have different categories of these particular things. So we're going to be drawing a bar graph that is going to be best suitable for this scenario here. So in drawing a bar graph or in drawing a graph, we have our y-axis and we have our x-axis. Remember that we need to label our axes, and this is our origin where the two axes meet. So on the y-axis, we have the expansion. That's in millimeters. That's the units that we are given here. And then on the x-axis, we have the material. So we are going to start off with the scaling of this graph, whereby we're seeing that the smallest number that we have is 10 and the biggest one is 19. So we can choose a suitable scale that we can use. So if we start from 10 and say 12 maybe, 14, 16, 18, and 20. So we have 12, 14, 16, 18, 12, 14, 16, 18, 20, and 22. In fact, you should be starting from 10 because our smallest number is 10. So we say 10, 12, 14, 16, 18, and 20. And then our different categories, we have brass as our first one. So if we have that, then it says that it goes all the way up to 19 millimeters. So 19 millimeters is halfway between 18 and 20. So we have our bar there. And then that's our brass. And then we have iron. And then our iron, it goes all the way up to 12 millimeters. So 12 is somewhere there. So we have 12 millimeters. This is our iron. And then we have steel that goes all the way to 11 millimeters, and 11 is halfway between 10 and 12. So we have our steel. This is our steel. And then we have platinum alloy that goes all the way up to 10 millimeters. So we have our platinum alloy that goes to 10. Remember that when we are drawing this particular graph, we need to use a ruler so that we can measure exactly where it goes up to our expansion. So that's going to be our platinum alloy. And then we have our ordinary grass. So we're just going to extend our x-axis. So our ordinary grass, it goes all the way up to 11 millimeters. So 11 is halfway through there, so it's the same as that, as our steel, because steel and alloy, they have the same expansion. So that is going to be our ordinary class, our OG. And then the last one is going to be concrete. It's also the same expansion as our ordinary class. Right. So this is going to be our concrete. Now, what we are noticing is that out of all these materials that we have here, the one that has the highest expansion is going to be brass. So that means if you were to use brass when you're trying to build something, or you're trying to fix something, or you're trying to decorate with brass, you need to make sure that you allow for a space of 19 millimeters for this particle when on a hot summer day or on a hot sunny day. For it to expand and contract, you need to make an allowance of 19 millimeters. And all the other ones, for iron, it's 12 millimeters. For steel, it's 11 millimeters. Platinum alloy, it's 10 millimeters. The ordinary glass and the concrete, they are both 11 millimeters. Make sure that you allow for that particular space for the expansion and the contraction of these materials. So this is our complete graph, but then remember that a graph is never complete without the following things. Number one, make sure that you have the correct scale as we have. Remember that you also need to label your axes, both the y-axis and the x-axis. And if there are any units for those axes, label them or include them, as we have here for the millimeters of the expansion. And then the last and also the most important thing again is the heading of that particular graph. So for this one, this graph is complete, just missing the heading. So our heading for this graph is going to be expansion versus different types of materials. Different So we start with our heading. Remember that the heading is going to be based on what you're going to be drawing. We're drawing the graph of expansion versus the different types of materials. You need to label your axes, the dependent and the independent variables, the y-axis and the x-axis. And then make sure that you also have the correct scale for your axis, if there needs be. And then also the units for each axis, if there are any units for those axes. Like in a case of materials there, we don't have any units, so we can just write materials. But for our y-axis expansion, they are measured in millimeters. So it's very important that you clearly show all those particular things when drawing the graph. So our next question now is, we are asked that which material expands the most and which material expands the least. So which one has a larger expansion or a greater expansion as compared to the other ones? So by looking at this table that we have, we are seeing that the one that expands the most is going to be our brass, because its expansion is 19 millimeters, which is way above all these other materials. So the one that expands the least is going to be our platinum alloy, because it's 10 and the other ones are 11 and 12 respectively. So to answer the question, we say which one expands the most? So the most expansion, that is going to be our brass. And then the least expansion, it comes from our platinum alloy. There we go. So remember that we are not just thumb-sucking these materials, we are looking at the table that gives us the correct expansion of each of those materials. So we're not guessing, we are reading every information that we have from the table that is given to us. So our next question says, which solid would be best suited to reinforce concrete? Give a reason for your answer. So which material is going to be suitable for the expansion of concrete? So we are given here, we have brass, iron, steel, platinum alloy, ordinary glass, and concrete. So our concrete expands up to 11 meters, right? So which one is it going to be possible, or which one is suitable for us to use in order to reinforce our concrete? So we need something that expands slightly bigger or slightly bigger than the concrete. If concrete expands at 11, the one that is most suitable to use to reinforce our concrete would be the iron, because its expansion is slightly above the concrete. So therefore, the one that you're going to be using is iron. And then why are we saying iron? Because its expansion is slightly above, so it allows for the expansion of iron. Concrete expands up to 11 millimeters. So the iron expands up to 12 millimeters. So it allows for the expansion and contraction of our concrete. So iron, it allows for the expansion by it being slightly above, by being slightly above the expansion of concrete. So iron would be the best suitable one for us to reinforce our concrete with. So question that is given again says, the diagram shows a metal ball and a ring apparatus. The ring and ball are both made of brass. At room temperature, the ball is just the right size to pass through the ring. So we're saying that at room temperature, the ball is able to pass in and out or to slide in and out of that ring. So question is, do you think the ball will still fit through the ring after it has been heated? So we need to know what happens to material when it's heated. So if material is heated, it expands by increasing the spaces between the particles. The number of particles making up that particular ball will remain the same. Just the spaces between the particles are going to be increased. So if the spaces are increased, the particle will appear to be larger because of the spaces between them. So when it becomes larger, it won't be able to pass through that ring. So therefore, no. Do you think the ball will still fit through the ring after it has been heated? No, because the particle will expand, or the ball will expand. The ball will expand. Remember, the expansion is caused by the increase in temperature, So question B says, do you think the brass ball will have more mass after it has expanded? Explain your answer. Remember, once we increase the temperature, the brass ball, the spaces between the particles that are making up that brass ball are going to increase. But the number of particles making up that brass ball will remain the same. So that means the mass of the brass ball will remain the same, just slightly increased in terms of the spaces between the particles. So the mass will remain the same because the mass is an intrinsic property. Unless I change the ball altogether and use a slightly bigger ball, then we can say the mass has increased. But if it's the same ball, then the mass will remain the same even before and after the change in temperature. I can increase the temperature or decrease the temperature. The mass of that particular ball will remain the same. Just the difference between those two scenarios is the spaces between the particles making up that ball. So do you think the brass ball will have more mass after it has expanded? No. The mass of the remains the same, only the spaces between particles will increase. So the mass remains the same, only the spaces between the particles is going to increase, and therefore it will appear to be larger, but the mass and the number of particles remain the same. So now, we are now going to move on to our application questions based again on the expansion and the contraction of materials. But before we do that, let's quickly go for an ad break, and I'll see you just after this.